Hi there, welcome back to my channel. If you have always wanted to understand and delve into the depths of Dijkstra's algorithm, then this is the video for you. Here is a weighted graph where each one of the nodes represents a town. The number that is associated with each edge between towns is the cost or the distance in miles between them. If our source node is C and the destination is E, what is the shortest path between these two nodes? In other words, what is the path with minimum cost between these two nodes? Now, there are multiple paths to node E, right? So, for instance, this could be one path. The cost of this path is 2 plus 4 plus 6 equal to 12. Here is another path, and the cost of this path is 5 plus 8 plus 3 equal to 16. And this is another path here whose cost is 2 plus 5 plus 3 equal to 10. So if you manually do the calculation, you'll see the minimum travel cost is 10. And how do we arrive to that answer programmatically? So this is the kind of problem that can be solved using Dijkstra's. That's why it's used a lot in GPS devices to find the shortest route from the current location to the destination. Dijkstra's algorithm finds the shortest distance between two nodes on a weighted graph. Conceptually, it is quite similar to a breadth-first search algorithm, although the key distinction is that breadth-first search works on an unweighted graph or a uniform cost graph. So for example, let's say the cost to travel between all nodes is 1. We could run a breadth-first search to find a shortest path in this case. I would highly recommend that you check out my video on breadth-first search if you'd like a refresher. During the traversal, we'll keep track of the distance cost to reach a particular node from the source node in a dictionary. We don't know anything right now, so we'll set their values to infinity or the maximum value possible. Once we discover their costs during the traversal, we'll set the values appropriately. We'll be using a min-heap data structure for the execution of Dijkstra's algorithm. Okay, so let's step through the algorithm. The gray color of the nodes indicate that they are undiscovered. Once we have navigated to it and are in the process of examining all the connections originating from the node, we'll consider that node discovered and change the color to orange. After completing the examination and navigating away from the node, we will mark it as explored and modify the color to green. In this algorithm, every time we process a node, we need to do two things. The first is to update the distance cost estimates of the connected nodes in the distances dictionary if it's less than its current value. The second is to choose which node to navigate to next. The node to navigate to next will always be the one with the minimum cost from the source node. We'll use a min-heap to make that determination, and you'll see how we do that in a second. Our source node is node C, and since we are starting from it, its cost is 0. We'll update that information in the distances dictionary. Since we are exploring node C, we'll change its color to orange and heap push a tuple containing node C and its cost to the min-heap. This way, our min-heap will always have the node with the minimum cost at the top. So this is where we'll start our while loop. While there are elements in the heap, we will heap pop the first element. Node C is connected to 3 nodes A, B, and D. The distance between C and A is 2 miles, and the current cost to reach C is 0. Therefore, the total cost to reach A is 2 plus 0, which equals 2. Since 2 is less than A's cost in the dictionary, we'll update the estimate to 2 and heap push it on to the min-heap. Note that the color of node A is changed to orange to indicate that it is discovered. The distance between C and B is 9 miles and the current cost to reach C is 0. Therefore, the total cost to reach B will be 9 plus 0 equal to 9. Since 9 is less than B's cost in the dictionary, we'll update it to 9 and heap push node B and its cost to the heap and mark it as discovered. The distance between C and D is 5 miles and the current cost to reach C is 0. The total cost to reach D is 5 plus 0 equal to 5. Since 5 is less than D's cost in the dictionary, we'll update it to 5 and heap push D and its cost onto the heap, marking it as discovered. Since we have finished exploring all connected neighbors of node C, we'll mark C as explored. As node A has the minimum cost, it is the topmost element in the min heap, so we'll heap pop it to process it next. The elements in the min heap data structure are not necessarily sorted, but anytime you heap push or heap pop, it will maintain the heap property of keeping the element with the minimum value at the top. In our case, the tuple containing the minimum distance will be the topmost or the first element. Please do check out the linked video in the description for a deep dive into the heap data structure. Dijkstra's algorithm is a slight modification from the breadth-first search algorithm. In breadth-first search, you also explore all the neighbors of a node, but then you would randomly pick any one of the neighbors. In this case, we pick the nearest neighbor. That is the only difference between the two. Let's examine the distance estimates of the unexplored nodes connected to node A. The distance from node A to node F is 4 miles and the current cost of A is 2 miles. So the total cost to travel to node F is 4 plus 2 equal to 6 miles. 6 is less than the current value of F in the distances dictionary, which is infinity. So we'll update F's cost to 6 and also heap push it onto the min heap and mark it as discovered. The next node connected to node A is node B, which is located 5 miles away. The current minimum cost to node A is 2 miles, hence the total cost to B is 5 plus 2 equals to 7. Since 7 is less than the current value of node B's cost in the dictionary, we will update the cost to 7. We will also heap push B and its costs of 7 to the min heap. With all connected nodes of node A examined, we'll mark it as explored. Now notice that there is already a value of B with a cost of 9 in the heap. This is acceptable because the cost is from a different route. From this current route, which is via node A, the cost is 7. Since 7 is less than 9, it will take a higher priority over 9. Now node D is the topmost element in the heap, and so we'll heap pop and process it next. Node D is connected to node B. The distance between D and B is 8 miles. The current cost of node D is 5 miles, so the total distance to node B is 8 plus 5 equal to 13 miles. Since 13 is greater than B's current cost of 7 miles, we will leave it as it is. With all neighbors of node D examined, we will mark it as explored. The next element with minimum cost is node F, and so we'll heap pop and process it next. The only unexplored node connected to node F is E, which is 6 miles away. Therefore, the total distance to E is 6 plus the current cost of F in the distances dictionary, which is also 6. So 6 plus 6 equal to 12 miles. Since 12 miles is less than E's current value of infinity, we will update the value to 12. We'll heap push E and its distance cost to min heap. We are done checking out all the nodes around F, and so we'll mark it as explored. The next element to process is node B, and we'll heap pop it. The only node connected to node B that is not explored is node E, which is 3 miles away. The total distance to node E is the current cost of B, which is 7 plus 3 equal to 10. Since 10 is less than E's current value of 12, we'll update E's cost to 10. We'll heap push node E and its cost of 10 to the min heap. We can now mark node B as explored. The next element in the min heap is node B with a cost of 9. However, since we have just finished exploring B, we'll simply heap pop this element from the heap and take no further action. We've reached the last stop, node E, with a cost of 10. Let's first heap pop it from the heap. Since it has no unexplored neighbors, there is nothing left to process, so we can mark it as explored. Let's then heap pop the next element, which is also node E. Since we just finished exploring it, we'll do nothing. So this concludes our Dijkstra's algorithm. Now, returning to our original question of the minimum distance needed to travel from source node C to the destination E, the answer is 10 miles. Here is a representation of the weighted graph that we just reviewed in the form of an adjacency list. The key is the node and its value is a list of tuples. The first element of the tuple is the node it's connected to, and the second element is the weight of the edge. If you'd like a refresher on graph and its various representations, please check out my video that I have linked in the description. So we'll be passing this adjacency list as a parameter to the shortest path function that we will review next. Before we review the code, can I please ask you to subscribe to my channel and give this video a thumbs up if you're enjoying the content of this video? Please do leave a comment if you have a feedback. Your support encourages me to create more videos like this and help others as well. Let's now review the code. The function shortest path will take three parameters: a graph, which is an adjacency list, source, and destination. We declare an empty dictionary called distances to track the distance cost to reach a particular node. We'll enumerate the graph's adjacency list to obtain all keys, which represent the nodes in the graph, and initialize them to infinity. We'll set the distance estimate of the source node to 0 and also declare a set called explored to track the explored nodes. We'll declare an empty list and call it heap. We'll heap push source and its distance to the min heap. The reason we are using a min heap is because we want to select the node with the shortest distance first. We'll continue a loop while there are elements in the heap. The first thing that we'll do inside the loop is heap pop the node. If the node is already in the explored set, we'll skip it and continue to the next element in the heap. Otherwise, we'll add the node to the explored set. Next, we'll iterate through each connected node and its distance in the graph. If the connected node has already been explored, we'll skip it. If the current node's distance plus the distance to the connected node is less than the cost of the connected node that we have recorded in the dictionary, we'll update that estimate in the distances dictionary. Then we'll add the newly estimated distance cost and the connected node to the min heap using heap push. And finally, we'll return the cost estimate of the destination. I've added a GitHub link to this code in the description. Please do check it out when you have a moment. Let's discuss the time and space complexity. If V represents the number of vertices or nodes and E represents the number of edges or connections in the graph, the time complexity is O of V plus E log V. The O of V plus E term accounts for traversing all the nodes and edges. Additionally, the log V term comes from popping and pushing all the vertices to the min heap, which is the time complexity of those operations. The space complexity is O of V because in the worst case, we could be holding all the vertices in the min heap. So with that, we have come to the end of this video. Thank you so much for watching it. I do look forward to seeing you in my next video. Goodbye.